Good afternoon, everyone. Today we're going to continue lecture series for Digital Electronic Systems 102. Today's topic is part delay reduction strategies for single precision floating point multiplier systems. My name is Dr. Marcus George. So we have 5 items to look at today. The first is an introduction to floating point numbers. The second is single precision floating point multiplication. The third is the strategy for part delay reduction of floating point multiplication. The fourth is an evaluation, very important evaluation of the effectiveness of the selected strategy. And the fifth is we're going to actually have a discussion of the impact of part delay reduction on the future of the region. So to better understand floating point numbers, it is wise to actually first look at what fixed point numbers are. Now, in fixed point numbers, the position of the decimal point remains fixed. So for a number like 12.875, representing that in 8-bit fixed point format, there are 4 bits before the decimal point and 4 after. So the answer is seen as 1100, 1110, easily understood if we actually have the decimal point in the middle. Now, floating point numbers, on the other hand, the position of the decimal point is variable and it depends on the number to be represented. Now, floating point format is very popular in digital systems, especially in the area of computer arithmetic, and we're going to see that just now. Now, a very big difference between floating point numbers and fixed point numbers is that floating point numbers, the dynamic range of numbers that can be represented with this format is significant compared to fixed point numbers, which is very limited. There are a couple of these 5 floating point representations that are going to identify. There are half precision, which is 16 bits. Single precision, which is 32 bits, and both of them are still very popular. Double precision, which is 64 bits, where a lot of processors are being built using this format. Quadruple precision and octuple precision. Quadruple is 128 bits and octuple is 256 bits. These are well documented in the IEEE 754 standard for floating point numbers, so you can check that out. Now, floating point, the IEEE 754 standard for 32-bit floating point numbers, it dictates that a single precision representation would have a sign bit, one sign bit, which will be bit 31. The bias exponent is 8 bits, and that will be bits 23 to 30. And a mantissa of 23 bits, which is bit 0 to 22. A total of 32 bits. It also dictates that a bias of 127 is utilized, and the bias is required to ensure that the bias exponent is unsigned. So let's do an example. Converting 23.875 to 32-bit single precision floating point format. Step 1 is to convert that decimal number to binary. So we end up with 23.875 to binary is 10111, decimal point 111. Second step is to convert that binary number to standard form. So we end up with what's on the right here and 2 to the power of 4, 4 being the exponent. The third step is to determine the sign bit. So the number is basically a positive number. If the number is positive, then the sign bit is 0. If the number is a negative number, then the sign bit is 1. So remember that. The fourth is computing the bias exponent. So before we had our exponent of 4. To get the bias exponent, we have to add 4 in binary to the bias, which is 127 in binary. That's going to be 4 in binary added to 127 is going to give us 131. So the bias exponent is 10000011, which is 131. The last thing we do is determine the mantissa. And anything after the point in standard form, the value of the binary number in standard form, anything on the right hand side of the point is going to occupy the most significant bits of the mantissa, as you can see here. Anything after that is going to be padded with zeros. The remaining bits are going to be padded with zeros. So at the end, putting all components together, 23.875 in floating point format, 32-bit floating point format is what we see here. Sign bit of 0, bias exponent, and the mantissa. So for homework, I want you to convert 23.875 to 64-bit double precision floating point format. Now, single precision floating point multiplication, that basically involves multiplying two 32-bit floating point numbers. And what we're going to get out of that is the generation of three components. Those three components we spoke about before, but for the product sign, which is going to be done with our lookup table, the product bias exponent, which we're going to do using our binary adder, and the product mantissa, which we're going to be doing using our binary multiplier. For those of you that cannot recall what binary multiplication is, we have to generate partial products and then sum them up. So we have two parts: multiplier. Multiplier is the second one here, and the multiplier is the first. We are going to multiply. Look at the least significant bit of the multiplier, which is in this case 0. And if it's 0, the partial product is 0. If it's 1, then the partial product is equal to the multiplicand at that instant. And after we calculate the partial product, we're going to actually shift the multiplicand bits 1 bit to the left, multiplier 1 bit to the right, so that we could conduct the next partial product operation. When we finish generate all the partial products, we're going to sum them up together in a binary addition operation. Now, before we go into strategies for path delay reduction, before anything, let's define what path delay is. Path delay is the time taken for a signal to travel from an input to an output of a digital circuit. Path delay has three components. It has the logic delay, which is basically the time taken to actually propagate through the logic gates. We have routing delay, which is the time taken to propagate through the wires that are connecting the logic together. And also we have clock skew. Clock skew is basically the spatial variation of the arrival time of the clock in an integrated circuit. So basically the largest contributor to path delay is basically the product mantissa generation. And that is done using a 24-bit binary multiplier. So if we want to have significant path delay reduction of the 24-bit of the floating point operation, the floating point multiplier operation, we have to target the mantissa generation component. And there are several ways to do it. The first is what we're going to focus on in this lecture, mainly the elimination of the partial product storage operation. It is basically taking a lot of that path delay to actually store the partial products, then retrieve them, and then sum them up. So if we get rid of that storage component, we can reduce the path delay. Also, handling of cases like 0 and 1. If I'm multiplying 1 by 0, the answer will always 0. Any number not multiplied by 0 is going to be 0. So therefore, if the multiplier or the multiplicand, any one of them is 0, we don't have to waste time going through the multiplication process. We could just output 0. Also, if any of them is 1, then there's only one value could be the product. If we multiply 17 by 1, the answer will always be 17. So in that case, we could avoid the long, lengthy operation. The last thing is multiplicand multiplier similarity investigation. If we have some information of what was multiplied in the past, we could easily retrieve the result, the product. So in this lecture, we're going to focus on path delay reduction via the elimination of the partial product storage operation. So this is the data path design for our binary multiplier system, 24-bit binary multiplier system with partial product storage. We use a RAM block to allow the storage of the partial products, and then we're going to have to retrieve the partial products from the RAM before we actually do the accumulation process. And that storage process is actually taking a lot of time. If we upgrade that to remove the partial product here, as you can see, the RAM block is removed, so we're not storing the partial products. Instead, we are actually going to accumulate the partial products as they are generated. So as they are generated, we're going to accumulate the partial products instead of storing them. And hence, at the end of the generation of the partial product process, we would have the final product. And this is what we want to do. Doing that, what that results in, it results in a significant reduction in path delay. And I have a side-by-side comparison of the initial system with the storage, partial product storage, and the final version, which removes the partial product storage component for a variety of platforms. Now, the variation in times basically is as a result of the variation in the architectures that we actually utilizing here. Also, other things like the physical silicon characteristics of the platform. So as you can see, the final version is significantly less than the initial version. And if I was to compare the path delay of the final version with existing systems by other researchers, we would realize that it also has a it's significantly less. The path delay of this multiplier system, final system, for the same platform with X4 is significantly less than Jane et al. 2012 and Arish and Sharma 2015. They both implemented 24-bit binary multiplier systems, and this implementation over here that I'm talking to you, the path delay is significantly less than what they have. So let's complete this lecture with a discussion on how the path delay reduction of the floating point multiplier system can impact the region. It can impact the region in many time-critical operations. And by reducing, and how it does that is by reducing the path delay of the associated calculations. So all of those systems will have either multiplier systems, dividers, all those kind of things involved in their system. And if we were to apply the same technique to those systems, then it would actually result in significantly reducing the path delays of those entire the implementations. As a result, we have systems like healthcare, emergency response systems, real-time patient monitoring systems. Those are going to be impacted. In automotive, we have things like driver assist systems, which require a lot of calculations, will be impacted. Autonomous vehicle control, industrial automation, robotics, process control, all those systems, and in telecommunications, real-time media streaming and video conferencing, all those things, all those systems will be heavily impacted, positively impacted by a reduction in path delay of the multiplier systems that are going to be used. So for the next class, we're going to be focusing on minimization using column maps. At this point in time, I'm going to open the floor for any questions.